So good evening to everyone. I welcome you all on behalf of Department of Mathematics, Wilson College, Mumbai. We have with us today as a resource person Dr. Anand Chitrao. Sir is a postdoctoral researcher in Department of Mathematical Science, Ulsan National Institute of Science and Technology, South Korea. Sir's research interest lies in numbers. So I welcome Sir on behalf of our college, and we are grateful that Sir has accepted our invitation and has agreed for a few sessions. So over to you, Sir.
Thank you, madam, for giving me the opportunity to speak in these sessions. Yeah, so let's start. Yeah, so the cursor is visible, right? Yeah,
Yes,
red
sir.
Yes, sir.
cursor. Okay, great. So maybe I'll start with basics today. Um, my plan is to first do some theory and then do some problems in the subsequent sessions. My aim is not to train you only to crack the JAM exam, but to train you so that after cracking the JAM exam, you'll be able to do well wherever you get selected. Okay, so let's start. Um, I'll be taking group theory. So let's start with the definition of a group. Uh, I know that some people are from SY or FY, so that's why I'll start from the definitions, the real basics. A group is a set G with a binary operation dot, usually denoted by dot, from G cross G to G such that following properties hold. Associativity, A dot B whole dot C equals A dot B dot C for all A, B, and C in G. Second property is existence of identity. I'll just write it as identity. There should exist an element E in G such that A dot E equals E equals E dot A for all A in G, and inverses. For all A in G, there should exist B in G such that A dot B equals identity, and so is B dot A. Okay. So does everybody understand what this means?
Yes, sir.
Yeah. So a group is a set G with a binary operation, means a function from G cross G to G, which takes as input two elements in G and throws out a single element in G. And this binary operation satisfies these properties. First property says that bracketing is irrelevant. The order of putting brackets is irrelevant. Second property says that there is an identity for the binary operation. And third property says that every element has an inverse. There's some doubt. Yeah, closure property is encapsulated here. So there's a function which takes two elements in G and throws out a single element in G. Okay, that answers one of the doubts. So what are some examples? Second point. Can somebody tell me examples of groups?
The N plus, then Z plus.
N plus is not a group, right?
Sir, under addition.
Natural numbers are not, don't form a group under addition. Yeah, but the second example that you said works well. Z comma plus. So to give a group, you have to specify a set and a binary operation. So the set over here is a set of integers, and the binary operation is just addition of two integers. Okay. So it takes two integers and just throws out. Um, there's some doubt. Identity A dot E equals. Oh, sorry. Yeah, there's a typo. A dot E equals E dot A for all the A in G. Thank you. So example is Z comma plus. This is one example. Then any others?
So Zn with addition modulo N, then Qnet group.
Yes. Zn with addition. Then related to Zn, there's a different group, right? What is it? Units Zn star under multiplication. Okay. So does everybody know what these two groups are? So Zn, you must have seen, this is the set of equivalence classes of integers modulo n. So you must have seen this set as written as 0 bar, 1 bar, dot, 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 n minus 1 bar. This set forms a group under addition modulo n. Okay. Next, Zn star, these are units of Zn. So this is all A bar in Zn such that A and N have nothing in common. The GCD of A and N is 1. Okay. So these elements form a group under multiplication mod n. So these three are some important examples of groups. Then after these come Sn. So does everybody know what Sn is?
Yes, a set of symmetric matrix. Permutation actually it is a bijection mapping.
Yeah. So Sn is a set of permutations of the set on n symbols, right? So this is, as you said, can be thought of as functions from 1 to dot 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 n to itself such that f is a bijection. So this is a group under which operation?
Composition of function.
Yes, composition of functions. Yeah. So if you take two functions over here, f and g, you compose them to get a new function. Turns out that's also a bijection. And so composition of function is a binary operation on Sn, and you can check these properties: associativity, identity, inverses. Okay. What's the identity in the group?
So when all the elements are mapped to itself,
Yeah, the identity map over here, 1 goes to 1, 2 goes to 2, dot, 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 n goes to n, that map is the identity for the composition operation. And inverses exist because functions are bijective. Okay. Next, let me tell you a nice way of writing elements in Sn. So, cycle notation. Let's do this with an example. Suppose you start with the set 1, 2, 3, 4. And with a function which sends 1 to 2, 2 to 3, 3 to 4, and 4 to 1. Suppose you start with this function which sends 1 to 2, 2 to 3, 3 to 4, and 4 to 1. Then this function is compactly denoted by an ordered tuple of this form. Start with 1, then look at where 1 is sent to under this map. So 1 is sent to 2. So 1 will be followed by 2 in this notation. Then look at 2. Where is 2 sent to? Sent to 3. Then follow that up with 3. Then 3 is sent to 4. So write 4 over here. Now 4 is sent back to 1. So instead of writing 1 over here, just close the bracket. Okay. Now suppose I have a different function. 1, 2, 3, 4. I mean between a 4 element set, which sends 1 to 2, 2 to 1, 3 to 4, and 4 to 3. Then this will be denoted by, start with 1, 1 is sent to 2, 2 is sent back to 1, so close the brackets. Now other symbols are remaining, so open a different bracket, start with the next symbol, 3, 3 is sent to 4, so write 4, 4 is sent back to 3, so close the bracket. Okay, is this clear to everybody?
yes, sir.
Yes, sir.
Yeah, you can unmute and say yes, everybody.
Yes, sir.
Yes, sir.
Okay, great. So everybody knows how to multiply permutations now?
Yes, sir.
Yes, sir.
Yeah, it's just composition. Now I'll give you the elements of the permutation in cycles and tell me what the product is. So suppose I start with 1, 2, 3 times 3, 4, 5. What is this equal to? So let me do this one for you.
So 3,
So what?
shall we start from 3?
You always start with 1.
In Gallian book, there is a product from right to left actually.
Yeah, but let's first do this. Let's first understand one method of doing this.
Okay,
So
sir.
how does one compute this product? You start with 1. Look at where 1 is sent to. So 1. So first apply this permutation. Okay. First apply this permutation. 1 doesn't appear in this cycle. Therefore, 1 is fixed by this permutation. So this cycle sends 1 to 1. And then this cycle sends 1 to 2. So in total, 1 is sent to 2. Then start with 2. This cycle fixes 2 because 2 doesn't appear here. Then 2 is sent to 3 by this cycle. So in total, 2 is sent to 3. Now see what happens with 3. 3 under this permutation goes to 4. And then this permutation fixes 4. So in total, 3 goes to 4. If you compute where 4 goes to, it goes to 5. Then 5 under this permutation goes to 3. And 3 under this permutation goes to 1. So in total, 5 goes to 1, which means it goes back to 1 here. So close the permutation, close the brackets. Okay, is this clear?
Yes, sir.
Yes, sir.
Okay. Now, um, can you tell me what's the inverse of this permutation? If you know the answer directly, don't say it out loud, but I'll give you a minute. In your notebook, you try to compute the inverse of this permutation. Inside S4. So it will be an element of S4. So try to see where 1 goes first. Open a bracket. Try to see where 1 goes. So ask the question, where should the inverse send 1 to? So that when you apply 1, 2, 3, 4, you'll get back 1.
So it's 4.
Yeah, the answer is 4. So start with 1. Suppose you send 1 to 4. Then this permutation sends 4 to 1. So in total, 1 will be sent to 1. So this looks good. Next, where should 4 go?
So it's 3.
Yeah, so 4 should go to 3. Because if 4 goes to 3, then this permutation sends 3 back to 4. And then 3 should be sent to,
2.
yeah, 3 should be sent to 2. Because then this permutation sends 2 to 3. And then 2 should be sent to,
1 again.
yes, back to 1. Let's close the parenthesis. Is this clear?
Yes, sir.
Yes, sir.
Yeah. Next, I'll give you 3 cycles. Tell me their product. Try to do this in your notebook and tell me the product.
Sir,
Yeah,
so 1, 3, 4, close the bracket, and 2 will be self-mapped.
yes. Why? So start with 1, then
1, 3, 4.
yes. Why is that? You start with 1, then this permutation sends 1 to 2, and this one sends 2 to 3, and this one fixes 3. So in total, 1 is sent to 3. Then start with 3. This permutation sends 3 to 3. This one sends 3 to 4, and this one fixes 4. So in total, 3 is sent to 4. Do the same with 4. This fixes 4. This sends 4 to 2, and this sends 2 to 1. So in total, 4 is sent to 1. So 1, 3, 4. And 2, as you said, 2 is sent back to 2. But if that happens, then we don't write it. We don't write anything. Okay? Is this clear to everybody?
Yes, sir.
Yeah. So let me tell you a shortcut of doing this. First, you note that 1, 2 is the inverse of 1, 2. It's a self-inverse element. Okay? So what we are doing here is conjugating 2, 3, 4 by 1, 2. So this product should be thought of as 1, 2, 2, 3, 4, and 1, 2 inverse. Okay? Then you just replace 2 by 1. Is that clear?
Repeat once.
Yeah. So this is something general. So if you have a permutation in the middle, let's call it sigma, and here you have a permutation tau. So tau sigma, tau inverse. Then what you do is just um, apply tau to all the elements appearing in sigma. You'll get a different permutation, and that is equal to this product. So if sigma is, let's say, 2, 3, 4, then this answer will be tau 2, tau of 3, tau of 4. Okay?
How this happens, sir, in general?
Yeah, in general, you write sigma as a product of cycles. In general, write it as a product of cycles. Let's say A1, A2, dot, 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 AK1, then whatever, B1, B2, BK2, dot, dot, dot. Let's call the last one C1, C2, CK3. And suppose you're conjugating all of these by tau, then the answer is just tau applied to A1, tau applied to A2, dot, 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 tau applied to AK1. That's the first cycle in the decomposition. Then tau applied to B1, tau applied to B2, tau applied to BK2, so on and so forth. Is that clear?
Sir, sound is not coming to me.
Is there audio issues?
No, sir.
Okay, okay. Try to turn on your speaker, try to turn up your speaker. Yeah. So if you are conjugating uh, an element of Sn, then this formula, I mean, you should remember this formula. There's a good way of quickly computing conjugates inside Sn. Then next is the group Dn. So let me write this down because sometimes notations confuse people over here. This is the dihedral group of order 2n. I'm following this convention that Dn is the dihedral group of order 2n. Okay. So this is again an important class of groups, and elements of Dn are of the form r power I s power j, such that r power n is the identity, s square is the identity, and sr s inverse is r inverse. Okay. So I gave a definition of a group in an abstract way. Um, every element of Dn can be decomposed as some power of r times some power of j, subject to these relations, that r power n is the group identity, s square is the group identity, and sr s inverse is r inverse. Okay. So some examples. So if you look at D3, D3 has a physical interpretation. D3 is equal to the, say equal to, yeah, group of isometries of the plane means R2, fixing a triangle. Okay. R should be thought of as rotation by 120 degrees, whichever way works, and S should be thought of as reflection.
Sir, sound is not coming, sir. I am rejoining.
Okay.
Instead of I am not listening to you.
Okay. Yeah. So D3 is a group of isometries of the plane fixing a triangle. There are many isometries. R is supposed to be rotation. R is supposed to be rotation by 120 degrees. S is supposed to be reflection along, reflection about the line passing through an altitude of the triangle. Okay. Equilateral triangle, of course. Yeah, sorry. I should be precise. And just to tell you, some magic happens over here, and D3 turns out to be equal to S3, isomorphic to S3. Next example is D4. This is the group of isometries of the plane fixing a square. Okay. So again, rotation by 90 degree, that's supposed to be R, and S is supposed to be reflection along a line passing through the diagonal. Any diagonal works. Is this clear?
Yes, sir.
Yeah. Then there are two really important examples. I mean, they are just a family of examples. G, L, and R under multiplication. So what is this group? Can
Gender
somebody tell
linear.
me?
So it's a gender linear group. It is a collection of those matrices whose determinant is non-zero.
Yeah. So
And
let's
the
say it
elements
in
come
this manner.
from field.
Uh-huh.
And the elements come from field entries.
Yeah. So uh, these are invertible n cross n matrices with entries in R. Okay. Over R, this amounts to the same as saying determinant is non-zero or determinant is invertible. Then, yeah, there's this example GLN FP. It's the same invertible n cross n matrices with entries in FP, where FP is the finite field with P elements. Is the same as ZP, but denoted differently, because when you write FP, you think of it as a field. When you write ZP, you think of it as an abelian group. You think of it as a group under addition. Okay. Are these two examples okay?
Yes, sir.
Yeah. So next, definition. Order of a group. So can somebody tell me the definition of the order of a group?
Total number of element in a group is said to be order of the group.
Yeah. So a better way of saying that is the cardinality of the group. A similar sounding phrase is order of an element. What is this? Can somebody tell me?
So the least power of element uh, whose order is equal to the order of the group. Then we say that order of an element.
What?
Sir, for any group, there is let's say there is an element A. So we multiply A with itself.
Mhm.
Uh, so up to n times, such that order of A is equal to order of the group. And when we uh, multiply A with itself, when we say order of A is n, that means when A is multiplied up to n minus 1 times, then we are not getting identity element.
Yeah. So order of an element A in G is a natural number such that A to the power n is E and A to the power n minus 1 is not E, right?
Yes, sir.
But seeing it differently, one can say that A power m is not equal to E for any m between 0 and n. Okay? Just to phrase it precisely. These are denoted by the same notation. So O of G and O of A. Okay? But the meaning will be clear whenever they are used. So some examples. What's the order of Z?
Sir, it is
Infinite.
actually to be undefined or infinity.
Yeah, so let's take it to be infinity. Then O of Zn is
N.
n. There are n elements in that group. What about order of Zn star? So Zn star consists of, is like all a's between 0 and n, which are co-prime to n, right?
Yes, sir.
Phi of
So
n.
have you seen? Yeah. There's a function in number theory called Euler's phi function or Euler's phi function or Euler's torsion function, and the cardinality of Zn star is that function applied to n. It has got a formula, and that's so phi n is equal to n times product over all primes dividing n 1 minus 1 upon p. Okay, this is a closed form of computing phi n. There are various properties of phi n, but we'll see them later. Then what's the order of Sn?
N factorial.
Yeah, why?
So it's a 1 1 n by onto mapping. So
Yes.
it gives n factorial mapping.
Yeah, why? So where can one go? It can go to any of the n elements, right? In the codomain. Once that is fixed, 2 can go to any one of the remaining n minus 1 elements. Then 3 can go to any one of the remaining n minus 2 elements. You multiply all of those, you get n factorial. So that's the answer. What is O of Dn? That's a tautology, because I
Twice.
define Dn to be a group of cardinality 2n, right? So it's 2n. What's the order of GLNR?
Infinite.
Yeah, it's infinite. Order of GLNFP. What about that?
So p so p raised to the power n minus pn minus 1 into pn and then minus pn minus 2 up to pn minus 1.
What? Can you repeat? P power n minus
P
hmm,
n minus 1. No, sir, in the power pn minus
yeah,
1. Close the bracket. Again pn minus 2.
yeah,
Then at the end dot dot dot. It goes like this, and at the end pn minus 1.
great. Yeah, linear algebra tells you how to compute this. So any matrix is constructed by linearly independent rows, right? So first you start with a non-zero row that is possible in p to the n minus 1 ways. Then you choose the next row, which is not a scalar multiple of the first row, that can be done in p to the n minus p ways, dot, dot, dot. That tells you how to compute the order of GLNFP. Okay, so that's great. Now, let's compute orders of elements. So what's the order of 1 in Z?
So infinity, because it's the
Yeah,
generator.
yeah. But using first principles, you can see that no power of 1 gives you 0. So this is infinity. Order of 1 in Zn is what?
N.
N. Because if you add 1 n times, you get n, but you cannot reach n or 0 in anything less. What's the order of 4 in Z5 star?
So it's 2.
Why?
No, sir.
You're correct. Answer is 2. Just give the reason.
Phi of 4.
No, answer is not 5 of 4. So using first principles, let's do this. So start with 4. Is 4 equal to the identity? The identity in Z5 star is 1, right? Is 4 congruent to 1 mod 5? No.
No, sir.
So you have to take its square. What's 4 square?
16.
16. 16 is 1 mod 5, right?
Yes, sir.
So 4 square turns out to be 1 inside Z5 star. So that means order of 4 is 2. Okay. What's
Yes,
the
sir.
order of 2 in Z5 star?
4.
Yeah, answer is 4 because 2 is not 1. 2 square is 4, which is not 1. 2 cube is 3, which is not 1. And 2 power 4 is 1. Then let's go to permutations. What's the order of this permutation?
3.
3.
Yeah, 3. What's the rule of computing order of a single cycle?
This is a total number of length.
Total number of elements appearing in that cycle, right? That's called the length of the cycle. Then what's the order of product of disjoint cycles?
To take LCM.
Yeah, this is the LCM. I'll write it down. Of orders of cycles appearing in that product. Okay. Yeah, these are direct formulas. One can give a proof, but I'll skip those. Let's move on to the dihedral group. What's the order of R inside Dn? If you remember, Dn is defined here. Dn consists of powers of R times powers of S, such that R power n is identity and no less, and nothing less. S square is identity, nothing less, and some relation. So what's the order of R?
N.
Yeah, n. What's the order of S?
It's 2.
2.
2.
Yeah, it's 2. And what's the order of RS? First, you have to see RS is not 0. RS is not the identity. The identity is R power 0, S power 0, right? So order cannot be a 1. Then try to take the square. So RS, RS. What is this? You note that order of S is 2. So S is equal to its inverse. So you can write this as RS, RS inverse. But you saw that SRS inverse is R inverse. So you get R times R inverse, which is identity, right? So what does this say?
2.
Order of RS in DNA is 2. Is this clear?
Yes, sir.
Yeah. Then let's move on to matrix groups. What is the order of this element? 0, 1, 1, 0. It doesn't matter. Inside GLNR, sorry, GL2R or GL2FP. What's the answer?
I think 2, sir.
Yes, 2. So this matrix is not the identity matrix, right? So the order cannot be 1, but if you take its square, you just get the identity matrix, so order is 2. This is called the long while element. Then try to compute the order of this element, -1, -1, 1, 0 in your notebooks. Here, do it. What's the square of that matrix? It's 0, 1.
-1, -1.
Yeah, -1, -1. What's the cube of that matrix? Multiply these two matrices. What do you get?
So 1.
And 0, because see, then 0.
Then 1.
Yeah. So order is 3. Doesn't matter if you're in R, doesn't matter if you're in FP, the answer is just 3. These two are interesting matrices, they'll show up later. So what's the order of 1, 1, 0, 1? Maybe I'll shift this. What's the square of 1, 1, 0, 1? If you compute, the square is 1, 2, 0, 1. The cube is 1, 3, 0, 1. The nth power is 1, n, 0, 1. Okay? So there are cases. The order is infinite if you are in G equals G ln R, and the answer is P if G is G ln, GL2, sorry, FP. Okay? So let's look at these orders again. So you can see that order of an element divides the order of the corresponding group in which that element is staying. Okay? Forget this infinite, these infinite cases. Over here, order of 1 in Zn is n, which divides the order of Zn. Then, if you compute these values, you'll be able to see that 2 divides phi of 5. Can somebody tell me what phi of 5 is?
It's
4.
4.
Yeah, phi of 5 is 4. 2 divides 4. Then here 4 divides 4. So you can see that orders of elements, they divide the order of the group. And here order of 1 to 3 is 3. 3 will divide S3. Cardinality of S3, right? What's the cardinality of S3?
6.
6. 3 divides 6. Or and it doesn't matter if you think of 1, 2, 3 is lying inside S3 or S4 or S5. The result is the same. Then order of R is n, which divides 2n. Order of S is 2, which divides 2n. Order of RS is 2, which divides 2n. So from this, you get some evidence of a theorem which says that order of a G inside capital G divides O of G if OJ is finite. Okay. So this is an important theorem because it has the following consequences. So if you start with A, which is co-prime to N, then order of A divides order of Z n star implies order of A divides phi n, which further implies A power phi n is 1 mod n, right? So this helps you compute residues mod n of powers of elements which are co-prime to n. And a baby version of this is if you start with A, an element A, and a prime P not dividing A, then A power phi P is congruent to 1 mod P. But what's phi P? What should I write here? What's Euler phi function applied to a prime P?
P minus 1.
Yeah. So this says A power P minus 1 is congruent to 1 mod P for any A co-prime to P. Okay. So this is really important. Then you get consequences like the following. So you saw that order of this element is 3, right? Order of this element is 3. Doesn't matter where, in which field these entries lie. So in particular, you can see that 3 divides P square minus P times P square minus 1 for all primes P. Okay. So just some application of this theorem. You must have seen problems like this. Show that some number divides P square minus P times P square minus 1 and whatnot. So this is one way of seeing that. Okay. Then this segues us into the concept of cyclic groups. Can somebody tell me what a cyclic group is?
A group is said to be cyclic if there exists at least one generator of the group.
Yeah. So a group is said to be cyclic if there exists a little g inside capital G such that given any G prime in G, there exists a n inside Z such that G prime can be written as G power n. Okay. So every element in the group can be written as a integer power of a single element. That this property is encapsulated into the phrase that little g generates capital G. Okay. So A group G is said to be cyclic if it has a generator. What are some of the examples?
Sir, Z,
Yeah.
then
And
Zn
yeah,
mod 1.
yeah, and no more. These are the only examples of cyclic groups. Okay. So there is a theorem which says that if there exists a little g inside capital G such that order of this little g is equal to the order of the group G, then G is cyclic. Okay. One can see easily that all powers of G less than OG are distinct. And there cannot be any more elements inside capital G. That's the proof of this theorem. Then the next theorem says, so yeah, just as an example, inside Zn, you have the element 1, right? Order of that element is equal to n, which is the order of the group. So you can see this theorem working over there. Next theorem says that Zp star is cyclic for any prime p. Yeah, the proof of this is not as easy as the proof of the first theorem, but yeah, you should remember that Zp star is cyclic always. And the next theorem is, yeah, Zpq star is cyclic for any two primes p not equal to q. Okay. To see this, one requires what is called as the Chinese remainder theorem, but I'll skip it. You can go take a look at it, and if you have any doubts, you can ask me next time. Then let's move on to a different class, a general class called abelian groups. Can somebody tell me the definition?
A group
If
gets
a
satisfied.
group is commutative, then it is known as abelian group.
Yeah, but what's commutative? What does that mean in
A
terms of elements?
dot B equal to B dot A.
Yeah, A dot B equals B dot A for all A comma B inside G. This property is said to be commutativity. If this holds inside the group G, then you call the group abelian. Okay, what are some examples?
Zn
Z,
plus Z, Q, R plus, H plus.
Yeah, Zn, Q, Z, R, C, FQ, FP, whatever you want to say. How about D2?
abelian, sir.
Yeah, if you remember, inside D2, the issue in Dn being abelian is this relation. SR S inverse is R inverse, right? But if R inverse happens to be equal to R, then this says that R and S commute, right?
Yes, sir.
So yeah, so that says if n equals to 2, then R, order of R is 2, then R is its own inverse. Then this relation says that R commutes with S. That says D2 is abelian. And then you can construct more examples on top of these. by taking direct products, if you know what that means, but I'll just write down Z cross Z. This just means you take the set, which is the Cartesian product of Z with Z, and operation over here, the group operation over here is component wise the individual group operation. Okay. So let me write down an important theorem. Every finite abelian group is of the form Zn1 cross Zn2 dot 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 Znk for some k greater than or equal to 1. Okay. So this theorem is useful in the classification of abelian groups of a given order. So can somebody tell me all abelian groups of order 4?
Z4.
Yeah, Z4 is one of them. Are there any
Z2 cross
others?
Z2.
Yes, Z2 cross Z2.
Klein's 4 group.
Yeah, Klein's 4 group is the same as Z2 cross Z2. So it's written as K4.
D2.
Yeah, D2 is also Z2 cross Z2. Okay, so there are only two abelian groups. In fact, there are only two groups of order 4 and they are Z4 and Z2 cross Z2. How about order 5?
It is Z5.
Yeah, Z5 is 1. Are there any others?
No, sir.
Yeah, so what you note is here every finite abelian group is of this form, right? What's the cardinality of this group?
N1 into N2 into Nk.
Yes, the cardinality of this group is the product of all these elements, since it's the same as the cardinality of the underlying Cartesian product, right? So it's n1 times n2 dot 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 times nk. So if you want to classify groups of a given order, abelian groups of a given order, then you take that number, you try to factor that as much as possible, and then try to place cyclic groups of orders equal to the factors over there. So when you start with a prime number, it cannot be factored, right? So there is a single group of that order, single abelian group of that order is a cyclic group of that order. How about order 6?
So Z6, D3, Z3 cross Z3.
I'm asking abelian groups. D3 is not abelian, right? D3 is
Yes,
not
sir.
abelian. Z3
Z2
cross
cross
Z3 is not
Z3.
of order 6.
Z2 cross Z3.
Yeah, so you can say Z2 cross Z3, but turns out these are the same. Again by Chinese remainder theorem. So an important fact over here is Zm cross Zn is the same as Zmn if m and n are coprime. Okay, try to see if you can prove this using this theorem. Then let's skip 7. How about order 8?
Z8.
Yeah, always start with the cyclic group, then
Z2 cross Z4.
Z2 cross Z4, then
Z2 cross Z2 cross Z2.
Yeah, Z2 cross Z2 cross Z2. Are these non-isomorphic pairwise? Can these two be isomorphic?
No, sir.
Why?
Because Z8 is cyclic, but Z2 cross Z4 is not cyclic.
Why?
Because Z2 cross Z4 has no element of order 8.
Yeah, so you can check that there's no element of order 8 here. That's why this is not the same as this. Why is this not the same as this?
Sir,
Again, the
in
same
Z2,
reason.
yes,
Yeah, go
sir.
ahead.
Yes, sir.
Yeah, the same reason. There is no element of order 4 here. And why are these not isomorphic? Why are these not same? Not the same group?
The same, there is no such element exist having order 8.
Yeah, there's no element in here of order 8. So there are 3 non-isomorphic abelian groups of order 8. Now, there is a theorem which is really useful uh, to show that a group is abelian if every element in G has order dividing 2, then G is abelian. Okay, remember this theorem. If the order of every element in a group divides 2, then G is abelian.
Sir, basically, this is the theorem similar to when all the elements are self-inverse, then it is an abelian group.
Yes. So order dividing 2 means for every G, G square is identity. G square is identity means G is G inverse. So there is a theorem. Proof is also easy. I'll skip it. So one liner. Let me tell you an interesting example of an infinite group. It has huge cardinality. So take the power set of natural numbers. This is the set. So I mean, this is really huge. This is cardinality even bigger than the cardinality of natural numbers. And under symmetric difference, this becomes an abelian group. Okay. What is the symmetric difference? Given any two subsets A, B of N, A triangle B is A minus B union B minus A. So you can see over here, it's easy to see that this is abelian, but you can also verify that in this group, every element has order dividing 2. So let me end with a few examples of groups which don't satisfy this property, the commutativity property, and those are called as non-abelian groups. So non-abelian groups are those groups which are not abelian. Obviously. So what are some examples? Can you tell me?
So
GLNR.
quaternion,
Permutation group.
Yeah. So Sn n greater than or equal to 3, then GLNR n greater than or equal to 2.
it is abelian.
What?
No, sir. I mean, Sn is actually I am talking about Sn when n is 1 and 2, then it is abelian.
Yeah, yeah. Then there's an important example, and somebody said that I think at the beginning. quaternion, a
Alan
group
Ford.
of quaternions. Yeah. So it has these elements. So you start with 1, minus 1, I, minus I, j, minus j, k, minus k. So 8 elements, and there are some relations. I square equals j square equals k square equals minus 1, and so is ijk. Yeah, these are the only relations, I think. So the resulting group is said to be a group of quaternions, order 8. And try to remember this group. This helps a lot in IIT JAM. For example, every proper subgroup of this group is cyclic. If you know what subgroup means, it will show up in the next lecture. And yeah, just to end with something. First non-abelian group appears in order 6. And what is that?
S3.
Exactly. Namely S3, which is the same as D3. And next ones, they appear in order 8. And what are they?
Quaternion.
Q8 is 1. And what's the other one?
D4.
Yeah, there are only 2, Q8 and D4. So, just to round up, there are only 2 non-isomorphic groups of order 6. They are Z6, the abelian group Z6, which is cyclic, and the non-abelian group S3 or D3. And groups of order 8, there are 5. So 3 of them are abelian, Z8, Z2 cross Z4, Z2 cross Z2 cross Z2, and 2 are non-abelian, Q8 and D4. Okay? Any doubts till this point?
No, sir. Sir, can you show me the definition of dihedral group?
Yeah. Going up. Yeah. The dihedral group of order 2n has this, what is called as its presentation. It's a group generated by 2 elements, R and S, subject to these 3 relations, that R to the n is E, order of R is order of R is n, order of S is 2, and SRS inverse is R inverse.
Okay, sir.
Yeah, one can relax this a bit. So you can assume that R has infinite order, and then you get what is called as infinite dihedral group. But yeah, I've skipped that.
Sir, here tau is the mapping now.
Yeah. Here tau should be thought of as the function sending A1 to tau of A1. Just some tautology. Sending A2 to tau of A2, dot, dot, dot. Yeah, try to remember this. This is really useful, this identity. Okay, that's all I wanted to say. There are no questions then. That's it.
Thank you, sir.
Thanks for attending.
Are there any other doubts, participants?
No, ma'am.
Hello? Okay. So thank you so much, sir, for such a informative lecture. Sir's next session is scheduled on Wednesday, 6 to 7. So we'll meet on Wednesday. Thank you very much, sir.
Thank you.
Thank you, sir.